Okay, so this lesson is about the chain rule, which is the big, most important rule for combining functions and how their derivatives work. So let me give some motivation behind it, and then sort of a mini quasi-proof of it, and then we'll do a few examples. So the motivation behind it is, what we want to do is we want to understand if I have a f of g of x, so I'm putting g inside f, and I want to take the derivative of this. The derivative of f of g of x. What is this going to be? How's the rule going to work? And the first thing I want to do is I want to say, well, what happens if f and g are linear? What if they're just lines? So what if f of x is like m1x plus b, and g of x plus b1, and g of x is m2x plus b2. So this is a line with slope 1, and this is a line with slope m1. This is a line with slope m2. And we know that the derivative of a line is just the slope. So the f prime of x here is m1, and f and g prime of x is m2. What if I do this? What if I put g into f? What is f of g of x? Well, that's putting this into that function. And so I will get m1 x plus b1. So this is f of x, and I'm going to put g of x into this. So where I had x in the f function, I write the g function m2x plus b2. If I simplify this, I see I get another line that distributes onto there. Then I get some constant terms that I'm not concerned with. And if you notice, the slopes have multiplied. So this gives me a hint that when I compose functions, the derivative, there's going to be some sort of multiplication of slopes going on here. But it's a little bit trickier than just straight multiplying the derivatives. This might lead you to think, so I'm just going to do f prime times g prime. It's kind of like that, but there's a catch. So let me see if I can justify the catch. So let's say now f and g aren't linear. So this is going to be my graph of f of x over here on the left. So let's say here's a graph of y equals f of x. And let's say here's g of x looks like something else. So here's the graph of y equals g of x. And I want to try to understand what is the derivative of f of g of x. And let's say I want to do this at some value. Let's say x equals a. So this, what does it mean to put a into this function before I think of the derivative? Well, it means I'm going to put a into g of x, and I'm going to take what I get from g of x. It's going to go into f. Let's look at what that would look like over here. So first I have g of x. So maybe a is right here. This is a. And so here we have this point here, and this is the point a, g of a. So when I do f of g of a, I put a into g, and I get g of a, but then I take g of a and I put it into f. So that means I'm not plugging a into f. When I do this composition of functions here, I'm putting a into g, but then I'm putting g of a into f, which means I'm not going to look at a here. I'm going to look over someplace else. I'm going to look like maybe g of a is over here. So here's g of a. And then I have this right here. This is g of a, f of g of a. Now, when I look really closely at each of these functions, they look like lines. If I zoom in here, this looks basically like a line. If I look really, really closely, it looks like a line. And we know the slope of this line is given by the derivative of g. But it's the derivative of g at this value, at a. And over here, when I zoom in on this function, it also looks like a line, if I look really closely. So I zoom in on it, and it also looks like a line. But here, so we know that slope is given by f prime. But here it's not a that I'm computing the slope. The slope is at g of a. That's a little bit peculiar. So I've got the slope of this line is g prime of a, and the slope over here is f prime at g of a. And using the idea that if we had lines, we could multiply the slopes, which was up here. Coming down here, I'm going to use the same idea. Up close, this looks like a line. Up close, this looks like a line. And I know that when I compose lines, I can multiply their slopes. And so this gives me at least a justification for the chain rule, which is the answer to this question is I'm going to multiply this slope times this slope. And this will give me, let me just scooch the paper up here a little bit. So the answer is it's f prime at g of a times g prime of a. And this is my first definition of the chain rule, my first way of writing it down. So how does it work in practice? I want to show you how it works in practice. See, the way it works in practice is tricky because we don't usually are given functions explicitly labeled as f and as g. So let me show you an example of where we might use it. Let's say I have a function h of x, and it is x squared plus 2x minus 3 all to the 4th power. And I want to compute h prime of x. Now, for the first and for the only time, I'm going to explicitly write out my f and g functions, because I think it's a very confusing way to do it explicitly like that. But here, if I look at this, my inside function here that was my g of x. And my outside function is what g of x is being plugged into. So what's being plugged into is it's being plugged into something to the 4th power. And so f of x would be x to the 4th. And so if I write them out like this, then h of x is f of x, f of g of x. It's g of x plugged into that. So the chain rule tells me from the previous page, says h prime of x, the derivative of this is f prime of g of x times g prime of x. And that is, so I need f prime and I need g prime. So f of x is x to the 4th. There's f of x, x to the 4th. So f prime of x is 4x cubed. G of x is this, x squared plus 2x minus 3. So g prime of x is 2x plus 2. And so following this formula, I get f prime, but not f prime of x, f prime with g of x plugged into it. So I get 4 g of x, x squared plus 2x minus 3. Then I have the cubed times g of prime of x, which is straightforward. And there's my answer. Now, this is extraordinarily difficult to do this way by explicitly writing out f and g and writing down f prime and g prime. So I'm going to show you a much better way. I'm going to do the exact same problem and show you a much better notational way of attacking the problem. And this is going to be our standard way of doing it in this class. So what you have to recognize is that this is a candidate for the chain rule. It's not one of our basic functions. Not if this wasn't here, it would just be a basic polynomial, and we would just use the power rule. Okay, but with this here, it's not a product. It's not two things multiplied together. It's not a quotient. If it's not a product or quotient, it looks complicated. It's going to be a chain rule question. So here's the way I want you to think about it. So you have to recognize that this is a polynomial plugged into something else. So what you can do, let me write out the chain rule again based on from the previous one. So the chain rule means if I want to take the derivative of f of g of x, I want to take the derivative of this, it's f prime g of x times g prime of x. So here's the way I want you to think about this. I want you to think of this g of x function as like a big U. So I want you to cover up the inside function with a variable. We'll just call it u. There's my big letter U. I'm substituting, I'm replacing, covering up this complicated inside function with a single variable u. Let's look over here. If I cover this with u, then this says f prime of u. So this is f of u. Let me cover this up for a second here. So if I had to take the derivative of f of u, it would just be f prime of u. Maybe I should have chosen different letters, but hey, we'll deal with it. If I had to take the derivative of f of u, I would get f prime of u. But the problem is that hiding underneath this is a function of x. And I'm not taking the derivative with respect to u. U is not the variable. The variable is x. So the chain rule says, after you're done taking the derivative of f of u, you then look at what u is covering up and you multiply by its derivative. This is u prime. This is the derivative of what was covering up. Let me show you this way of thinking over here. It's a much more fruitful way than writing out f's and g's explicitly. Let me show you. So I'm going to see h of x is something that I've just called u to the fourth power. And then I look at this and I say, well, I know how to take the derivative of u to the fourth. The derivative of u to the fourth is 4u cubed. There we go. Now the issue is u is not the variable here. This is h prime of x. X is the variable, and the u was covering up this. So the chain rule says, after you're done taking the derivative of this thing, you then multiply by the derivative of the thing of u itself. So then I have to multiply by u prime. And then I look back and I say, so this is 4, what was u? Well, u underneath here, you can see it underneath here, is x squared plus 2x minus 3. So I have x squared plus 2x minus 3 to the third. There's the u times, and then you should, if at all possible, if this is simple enough, do this in your head, the derivative of u itself. I can take the derivative of this in my head. This is 2x plus 2. And that's the derivative, and that's what the same answer that we got before, writing out all the f's and g's explicitly. Let's do another one or two examples. Okay, and I will look up some more examples for you if you want to see more. There's lots of examples. I've looked at a few videos that some other people have made that are quite good with these ideas. So let's do a square root. Square root of 1 minus x squared. This, by the way, is the top half of the unit circle. That's what the graph of this would be if I did y equals this, as a side note. So let's say I want to take the derivative of this. So it's not just root x, it's root something complicated. It's not a product or quotient, so it's almost certainly going to be a chain rule. So I recognize this is square root of some messy thing. So I cover this messy thing with my variable u. There we go. I'm going to cover it up. So now this is u square rooted, or u to the 1/2. So I'm taking the derivative of u to the 1/2. And I'm writing this u in red to remind myself u is actually covering up something else. Well, this is a power rule, so this is 1/2, continue with the red, u to the minus 1/2, and then the chain rule says now I need to multiply by u, wrong color, u prime. This is how the chain rule works. If this were merely x to the 1/2, then I would write 1/2 x to the minus 1/2 and I would be done. But since this is covering up some other function of x, I say, okay, so I do the normal derivative rule and then I multiply by the derivative of that thing that was being covered up. So what was u? Well, u, I can see underneath here, that's x squared.
So I'm going to get 1/2 1 minus x squared to the negative 1/2. That's just u, no derivative of u. This is just the derivative of u to the 1/2. Then I multiply by the derivative of u, and I can do that in my head. The derivative of 1 minus x squared is minus 2x. Or, if you want to simplify this, I'll let you think about why this works out to be minus x over the square root of 1 minus x squared. Okay, one last example. I'm going to link up a few more, and I'm going to talk about Leibniz notation of this. But let's do one more example. Let's do one where you have to bring in the product rule as well. Not too complicated though. X squared square root 1 minus x. So this is getting a little bit more complicated. X squared times the square root of something that's not just x. And so when I analyze this, I'm like, oh wait, this is a product. I've got x squared multiplied by square root 1 minus x. So it's going to be my a for the product rule. This is going to be the b. And I remember the product rule, if I take the derivative of a times b, it's the derivative of a times b plus the derivative of b times a. So I'm going to apply that over here. So the derivative of a is simply 2x. And then I have b, no derivative, plus the derivative of b. Well, that's the derivative of this. So I'm not going to try to do that in my head. I'm going to just write derivative of, and I'm going to write this as 1 minus x to the 1/2 because I'm going to have to take a derivative. And then I have a times x squared. Now I have to work out this derivative. And this is a little tiny chain rule hiding in here. It's not just x to the 1/2, it's 1 minus x. So again, I'll cover this with a u. And then I will recopy this. I'll recopy that. The chain rule tells me, so I have u to the 1/2. So I take the derivative of u to the 1/2, and it's 1/2 u to the minus 1/2. And then I have to multiply by the derivative of this u. This is the chain rule. I would like to just stop here, but this is not x. This is not my variable. This is not the variable I'm taking the derivative with respect to. This is some other function. And hiding underneath this u is 1 minus x.
And so I have to multiply by its derivative times u prime. And then u was 1 minus x. So I get plus 1/2 1 minus x to the negative 1/2. U prime is easy. The derivative of 1 minus x, the derivative of 1 is 0. The derivative of minus 1x is minus 1. Then I have times x squared from right there. And there it is in all of its hideous glory. One last quick note about this. It's a really nice benefit of the other notation for the derivative. Okay? It's not a notation. Let's say I have y is a function of x, but then x is a function of some other variable, maybe t. When I ask the question, what is dy dx? What's the derivative of y? Oh, not dy dx. What is the derivative of y with respect to t? Y depends on x. Y is a function of x, but x is a function of t. What is dy dx? Well, if I think about the chain rule says I'm plugging, oh, I don't want to use f here, g, there we go. I want to use the same letter. Sorry. Y is a function of x, x is some other function of t. So if I think of the chain rule says that if I want to take the derivative of f of g of t, that's f prime of g of t times g prime of t. But if I compare f prime of g of t of x times
g prime of t, we're mixing variables here. But the nice thing about this is a very nice way of writing this that looks beautiful. And that's dy dt is this times this. But this is just dy dx, the derivative of y with respect to x, times, and g prime of t is just the derivative of x with respect to t. And so you have this lovely cancellation of infinitesimals when you use this notation for the product rule. It's very nice. We'll come back to this when we do some different types of problems. This is a really nice notation, a nice useful way of thinking about the chain rule. Anyhow, that's all for now.